Now we're going to take this concept and we're going to consider a slightly different situation. Let's consider a stationary observer. Mission control, he's sitting in his control tower, and we have a flyby of a spacecraft. But instead of starting out at rest, this spacecraft is already at the speed of light and then continues onward to an instantaneous speed. Now I find it curious that Einstein never considered this, or at least I'm not aware if he ever did that. So if you know of any reference where he considered faster than light travel, go ahead and leave it in the comments section. So for right now, we need to back up and we need to talk about how the topology of space-time will change for a faster than light object. So again, I have this little animation here. We have our time axis that goes vertical with our two spatial axes. And now there's a red line here, and we're going to assume that we have a spacecraft capable of traveling and exceeding the speed of light. Now what will happen is, remember that the astronaut on board this spacecraft is carrying a clock with him. So the question is, how do we draw a time axis for this rocket ship once it has exceeded the speed of light? So in the previous animation, we saw that when the velocity of a spacecraft is below the speed of light, the time axis remains inside the light cone. What we'll see here is that once the spacecraft has exceeded the speed of light, the time axis is then going to be outside the light cone and its spatial axis will be inside the light cone. So essentially the time and spatial axes will have swapped, and one will be the spatial axis will then be on the inside of the light cone, whereas the time axis will be on the outside of the light cone. So here I made this cool little animation. You can see the rocket ship shooting off past the light cone, and what we have is the space axis now lies within the light cone, and the astronaut clock is now outside the light cone, which then indicates that that temporal axis, or that time axis, must be outside the light cone for a faster than light object. Now let's go back to the topology of space-time, but in this case, instead of making time slices on the time axis for the stationary observer, we're going to make slices along the spatial axis for the stationary observer. So in this animation, you'll see that I've flipped the light cone on its side just for presentation purposes, just to make it much more clear. And you can see that as we start slicing along the spatial axis and that's going to be related to the same time component, we get these hyperbolic wave fronts that form. And that means that the topology for a faster than light object is not going to be based on circular wave fronts, but they're going to be based on hyperbolic wave fronts. And that's because, once again, the time axis for a faster than light object resides outside the light cone. Now, like I was saying, we now have the same triangle, right triangle that we had for the slower than light object. However, the relationships between the hypotenuse, tangent, are all going to be different. We use the Pythagorean theorem for a unit circle for lower than light speeds. In this case, we're going to use a unit hyperbolic tangent function to relate each of the legs of the triangle. Now, once again, we're going to imagine that the rocket ships are traveling at the speed of light, and they zoom past a stationary observer, and they can continue onward to an instantaneous speed. So there's the rocket ships that go by, and we have the two light pulses. One light pulse obviously is how a moving observer would see it transmitted from one spacecraft to the other, whereas the stationary observer will see sort of a diagonal track of the light pulse. So once again, you'll see there, I'll just play it one more time here. There's the spacecraft, they go zooming by, and the light pulses meet together. Now we can also reverse this and instead of having it go from left to right, we can have it go from right to left, and it doesn't change the algebra or the geometry of it. Once again, the spacecraft zooms along. He or she emits a light pulse. It's intercepted by the other spacecraft. So now the three legs of the triangle are now represented by a unit hyperbolic curve. And in this case, we have the hypotenuse squared times the tangent squared minus the vertical distance that is traveled. We can then also plug in the clocks. In other words, we take these distances and we want to see how the clock for a fast and light object compares to a clock for a stationary observer. So once again, we get a similar kind of equation like we did the first time, but notice that the ratio of velocity to the speed of light now has been reversed. You now have it minus 1, and this also gives us a Lorentz type term, and I've defined this to be the tachyon Lorentz term. And what this indicates is that the fastest speed we can have is an instantaneous speed, and the slowest speed that it can have is at the speed of light. So this almost contradicts the first assumption, that is that nothing can travel faster than the speed of light, where in this example it shows us that nothing can travel slower than the speed of light. So when a particle is traveling at a faster than light speed, we call it a tachyon. I'm excited to announce the premiere of my new documentary film, Time is a Fluid That We Ride to the Stars. In it, I discuss how we will design and build a micro warp drive engine that will take humanity up to speeds faster than that of light. Be sure and hit that notification bell and subscribe button so you'll be alerted to when it's available. Until next time, see ya on my channel, Hyperdrive X.